So our next presenter is from Systra's Australia-New Zealand team with a case study on applying human factors tools and methods to the design of a train control system. Jan Asmussen is a senior human factors consultant with over 9 years of experience in the rail industry. Jan has been involved in a number of technically complex initiatives, including the rollout of ETS Level 2 digital systems and the introduction of remote switching. His portfolio spans numerous train control and signalling projects across Australia, where his human factors expertise helps enhance system usability, operational performance and safety in complex rail environments. In the background, in a supporting role, who may pop in for the Q&A if there's questions on this one, is Kate Moncrieff, who is the Director of Human Factors and currently leading the New South Wales Systems Engineering and Integration team for Systra Australia, New Zealand. And Kate has 18 years experience in rail with success in integrating human factors across complex projects. And Kate has extensive experience in managing human factors delivery, technical integration and assurance. But Jan is going to be leading this one, so I'm going to hand over to you.
Cool, thanks Fiona. Hi everyone, thanks for letting me present today. So I'll start off with the introduction. So essentially what we're looking at today is the Shepparton train control system. So it's essentially an HMI design report or project. I'll just give a quick brief overview of the project itself. For those who are interested or not aware of this project, it's called the Shepparton line upgrade. It's been through multiple stages. So at the moment, at the end of stage 3, Systra have been involved in each stage in some capacity. Stage 3 specifically is focused on signaling design upgrades. Stage 2 is mostly around like infrastructure and whatnot. So it's essentially a classic regional rail revival type project where you're increasing services between, you can see Southern Cross and Melbourne up to Shepparton and back down. So almost a doubling of services in both the up and down from about 5 to about 9 services, so essentially twice as much. So pretty big project. Right, so I'll move on to the next bit. So essentially what we did, so when we came in, was in the first instance to understand what are the actual changes being introduced by the project and what the impacts are, because that's what then helps us identify what are the best HF methods and tools, that are amenable to reviewing and assessing these changes and the impacts to provide that level of assurance that's required by the project to say, to basically provide the evidence, is this design acceptable or not for the end users and the intended use. So the 5 high-level or main changes were an extension of the TCS, which is the train control system called SIGVIEW, extending that across a wider area of the network, reduces train order working in those more remote areas. Train order working obviously has a pretty manual, onerous process, a lot of verbal paperwork, etc. Improve situational awareness with this new digital system. Then we have the introduction of the electric code, which is, I'll explain that a bit later in more detail, because that's one of the examples that we're looking into. So that's to do with latency for setting and canceling routes and some new failure scenarios. Then there's also the introduction of the slot. Again, I'll go into more detail on the slot because that's our second example. But essentially there was additional tasks related to operation and interpretation of the slot mechanism. And then we had new signaling equipment, such as interlocking new track sections. So there's some failure scenarios associated to that. And then, as I mentioned previously, an increase in train service. So, more routing, more train routing and regulation and management of trains. So yeah, we basically, together with the project engineers, identified what the changes were, the impacts, and then that's how we then kind of decided on what methods and tools we should use to apply to the work that we were doing. So yeah, in the next few slides, I'll highlight what those methods were, and just to show how they were suitable to helping us provide that assurance for the system and the technology that we were looking at. So right, example 1, as I mentioned, the slot. So I'll just briefly explain for those who don't know what a slot is. A slot is essentially a mechanism that manages the movement of trains onto a bidirectional single line between 2 different signaling areas. So you have signaler A, signaler B. They've got a straight piece of track. It's bidirectional, and only one train can go in at a time. So this slot helps manage the train moves into that section so that only one train can be going in at a time. in one direction, essentially. So it kind of replaces, no need for verbal communications and whatnot. It's essentially like a handshake between those two signalers sitting in different areas, managing their own areas of control. So essentially what we did was we needed to provide HF analysis to basically show that this design is acceptable and it can be interpreted by the user, provides them with the right level of information, they can use it, etc. And as you can see, it's a pretty complex and not necessarily immediately intuitive design. The different color lights, and they each kind of light up depending on different circumstances and different scenarios and what's happening with the system, what's the user doing. It also provides them with information, what can and can't they do in terms of what route can be set, what route has been set, et cetera, et cetera. So it goes on. And this is a static image. So these are the types of images that we were actually provided on the project to help to do our analysis on. So we didn't have a demonstrator or any dynamic environment to use to discuss with end users, elicit the system feedback, explain the behavior, et cetera. It was all with static images, and that was just the nature of the project and what we were working with. So that also kind of drove the types of methods and tools and approaches that we applied, which I'll get into in a bit more detail as well. Yeah, and I'm sure a lot of you on the call are familiar with this type of information being provided. A lot of static images are not necessarily the full set of how the system actually behaves. So you have to do a lot of work to understand the system, understand the behavior based on some of these static images. So it's quite yeah, it was interesting, our approach on that. So I'll move into the next bit around, as I mentioned, not as I mentioned. So one of the first steps we did was defining the types of scenarios. So looking at, what are the type here, we call them tasks, but these are essentially the different scenarios for this that are related to this indication. So again, working together with the project engineers, technical SMEs to kind of identify all the possible scenarios and use cases that are relevant for that indication, where the user would need to, interpret or use that indication to do their tasks or, carry out these scenarios. So we identified 4 in total that were relevant to the slot. So there's setting the route, both in the up and the down. Then there's a local signaler. So the local signaler is the one who sits and controls Seymour. And then we have the train controller who sits in Melbourne. So they're called central. So they're the central controller that control a wide area of the network. Seymour is a local signaler, and they're just controlling their own local area over in Seymour. So the local signaler can, turn a train back somewhere around here, and that was a scenario that wasn't initially identified as relevant, but through the work that we did, this was through engagement with the end users, we identified that this would be a viable scenario that we would need to look at to understand how that all works. And then we also had route setting when interlocking is disarranged, was essentially a failure scenario. But for the purpose of today, I wanted to focus on just the tasks or the scenario of setting the route. And we'll just work on the next few slides. We'll work together through, what our thinking was, how we approach this, what types of questions were we looking to answer, things like, what is the indication used for, how does the user use that indication, what information does it provide to them, what information do they need in order to carry out their tasks, and what other information is available on the system. You can see here, this is a classic track layout diagram, which provides additional information in addition to the slot indication. So all this information, how does the user use it? Is it enough information for them? Can they interpret it? Things like that. And what we did was we used a human error analysis, so essentially a Sherpa, to structure that analysis to look at all this different types of information. What are the tasks? What are the critical, high safety, high operational impact tasks, if there were any? What are the consequences? And then, identifying what types of controls are in place already through the design, or where the design might need to be changed to mitigate or manage these errors that we identified through the application of our HEA. And we've just provided a very simplified excerpt of the HEA just to show, what the task was, the roles involved, and, just a description of the types of errors that we identified, and then the consequence. And then that's how we then, work through to identify, all the different system behaviors and the controls or design elements that either helped or were required or necessary to help manage these or mitigate these errors. just a bit more technical detail here for those that might be interested. So essentially, this was the first task, which was setting a route in the down direction. So down being from left to right. So this is where the local signaler at Seymour needs to set a route into the down direction over and through the slot to then send the train onwards into Nagambie and then further on downwards. So in the first instance, the train controller, sitting in Melbourne, Central Command, essentially needs to set the slot to the reverse position here. Reverse is equivalent to the down direction, going to the right. And then on the local signalers panel, they have this color light panel with two directional arrows and the central circle in the middle. And then those lights or bulbs flash, illuminate depending on, in the first instance, if the slot is set to the down, that down arrow will illuminate the circle. That indicates to the local signaler that the train controller has set the slot to the down, which means, okay, that means that now my train, which is sitting on road 3, I know my timetable as a signaler. I know this train needs to go from Seymour down to Nagambie at a certain time. That slot is now in the down direction. Okay, local signaler knows that. And then when the local signaler sets their route, then on their panel, this color light then illuminates yellow. That tells the local signaler, okay, my route has been accepted. Meanwhile, the train controller can see this on their train control system. So this is what this TLD is what the train controller sees. So they can see that the local signaler has set the route. The route is now set and locked, which is the yellow indication. That tells the train controller, okay, I need to set my forward route on from SCR 66, which is the first signal that the train controller has control over. They set their route from 66 on through to Nagambie 30 into the platform. And then once that forward route is set, then the whole route is then set, goes green, signals clear, and the train can then traverse the route. So it took us, there was a good amount of HF, analysis together with the signaling engineers, the technical SMEs, as well as, of course, the end users. So a lot of robust discussion with the end users to really understand how this works and to really work through, do these indications, provide you with that information that you need to be able to carry out the task of setting your route and, with no issues and no confusion potential. So the same in the up direction, I won't go into too much detail, it's essentially the same, but in the reverse direction, again, train controller sets to normal, which is the up, train controller sets the route, and the color lights now are telling the local signaler that, oh, I shouldn't be setting any routes in the down direction because the slot has been normalized. Now routes need to be set in the up direction. And the the interesting thing here is that the this illuminated circle in the middle will be extinguished if any routes are currently set in the down direction. So that provides the local signaler with kind of the information that, okay, maybe I have a route set here, I need to cancel that route. Only when I cancel that route can then the slot offer be normalized in the sense that now the up route is set, this circle illuminates, okay, now that slot is completely blocked off. I can't set any routes in the down. I'm waiting for that up train to come through. So, and that also tells the local signaler they need to set their route from SCR 62 into whichever platform or road that train needs to go into, either, road 3 or road 1 down here. So again, that's kind of the interplay between information and really understanding how the user is interpreting that information and what do they actually do with that information in terms of the tasks that they need to carry out. So that was essentially what we went through with looking at, all the different scenarios and tasks related to the route setting and the information provided by the system. And then essentially the outcome was we did change one thing with the design. As I mentioned here, this slot indication, which is a digital switch on the train controller's HMI. The N and R are equivalent to, as I said, up and down. So essentially it was a pretty simple fix, easy win to change the N to up and the R to down. So then that more closely aligns with the mental model of the train controller, up, down. Very simple to then know which position the slot is in and which position the slot should be changed for the direction of the intended move. So that was a pretty simple one. And then the local signalers control panel And the slot indication, no change to that one based on our human error analysis that we conducted, as well as the HMI analysis, which was a complement to the HEA, where we essentially looked at, 4 classic heuristics from 11064 standard, classic HF standard. So looking at, information requirements, as I said earlier, what type of information does the user need in order to carry out their tasks? Mental models, does information align with how the user is interpreting and understanding the information to use? Information coding, that's, to do with, like, in this case, the color yellow being used for the lights, aligned with their understanding of the use of color yellow in the other aspects of the system. And then, of course, error tolerance, which is closely linked to the human error analysis that we conducted. So that essentially rounded out the analysis for us to then essentially demonstrate the slot indication and user interpretation and the operation of the slot was acceptable, and that provided that assurance to say, yeah, design is okay with that one minor change that I mentioned earlier, and all that provides that kind of robust assurance evidence. Cool. Then another, just example 2, as I mentioned earlier, we were looking at this electrocode system, which has an inherent latency associated to it. And the electrocode is used where 2 interlockings are speaking to each other, and one interlocking sends the message to the other interlocking, and then that other interlocking has to then send a code back. So that takes upwards to 30 seconds for that to go back and forth, essentially, for the route setting scenario. So you can already imagine a train controller setting a route from, say, Nagami 10 to SCR64. It'll take up to 30 seconds in the worst case scenario for that route to set, because those codes have to go back and forth. There's a whole very complex technical reason how those codes work. There's a million different codes and whatnot. We won't get into that, but essentially those codes need to go back and forth. So within those 30 seconds, what happens? What information does the train controller need in order to understand what's happened once they set the route, and what's going to happen? What are they expecting to happen when that route then gets set? And what indications are provided to them to let them know that the system is processing what they just, the command that they just executed or entered into the system, which was setting the route. So again, it's looking at, what system feedback is provided. Does the system support the user to understand what's happening? Is it keeping them in the loop? And do they know what's going to happen as an output of their actions that they've entered into the system? It's also worth noting another interesting bit here was this electrocode is only on certain areas of the network. So this behavior only happens in this area. If the train controller sets a route in another area, it'll behave, it'll be almost near instantaneous with the route set. So they won't see this flashing indication, which I'll talk about now. So again, it's understanding about, let's call it negative transfer, where, it's one thing happens this way in this area, and then in this area, completely different. So again, it's understanding system needs to provide them with the feedback to know that it's different in this area and what's happening and what to expect. Cool. So as previously, so again, firstly, just defining the scenarios. So in this one, setting a route, obvious, canceling a route, and then stacking the routes in the electrocode. And we'll focus on the setting a route for this one. And again, asking ourselves the same types of questions. What's the information used for? What information does the user need? How does the user know that the route request is being processed, et cetera? So those are the types of questions that we need to answer. And the same structure as previous, we're doing our human error analysis, identifying all the tasks, all the types of potential errors. User involved. In this case, it's just the train controller, so there's nothing to do with the local signaler. The types of errors we identified, consequences, and then looking at, okay, what in the design needs to change, or is the design acceptable to manage those errors or not? So that's essentially what we work through. Again, extensively work with the signaling design engineers to understand the system behavior. Again, working with static images. A lot of this is done in PowerPoint, where we're dragging and dropping, the route indications and adding, flashing yellow, pointing to where it's going to flash. So this is the level of fidelity that we were working with, which was tricky at times. try and convey this information and understanding to eliciting valid feedback from the end users and really understanding how does this actually work. So that was interesting. So essentially to talk through this one. So originally you could see in the previous slide it was flashing green. So essentially it went from, I'm pretty sure it was no flashing indication to flashing green to then actually ultimately the design was then a flashing yellow. And the reason for the flashing yellow is this was identified through our HMI analysis and the HEA, looking at color coding and mental models and the heuristics. Flashing the color yellow means already was already a color used in the system, and it means that the root is set and locked, bottom left here. So if this were flashing green, then the end user might expect, or the train controller might expect, the root to go from flashing green to solid green, but it could actually go from flashing green to solid yellow, which could potentially be confusing because the user might be expecting it to just be set and for signals to start clearing. But actually, in order for signals to clear, as I mentioned in a previous slide, there needs to be a forward root set as well. So in this case, here there is no forward root set, so this flashing yellow would go straight to a solid yellow. So again, it made sense to have that color align with the mental model that the user might be expecting, and the yellow being the lowest, let's say, like the lowest form of the root setting type, because then they'll need to set their forward root for then the root to be set and cleared, and for those signals to then clear and for the train to be able to traverse the route. And then there's also a route failure scenario where, for whatever reason, if there's an interlocking failure or some kind of failure, then the route would go from flashing yellow to the route occupancy, which is the red, which is displayed as a red track occupancy, which is pretty standard across signaling systems. So again, this flashing yellow indication kind of aligned with the mental model of the different types of routes and indications that the train controllers were already used to. And we did work. Our HF analysis then also showed looking at the different types of system behaviors and what's happening in the background. How long the flashing yellow indication. How long does it take for the system to process the route, and what are the possible outcomes of that? That all fed into this understanding of the analysis and working through with the end users to really understand what their mental model was for route setting, and how the design and the information provided by the system, how that supports that for them to correctly interpret it and make the right decision. And also that one of the consequences we identified was train controller potentially assuming that there's been a failure or something because they're not getting any information, and they revert to train order working, or they start trying to start the maintenance rectification process, failure rectification process, things like that. So again, going back to really good system feedback to provide that information to the user. And the outcome was, as I mentioned, the route setting indication changed, and then as you can see here, this was our HMI analysis against the 11064 heuristic principles that we identified as relevant. Yep. So I don't realize how much time. Yeah, almost on time. So summary of lessons learned. So this project was quite similar to other projects that we've undertaken, where we've identified common themes coming out of the analysis that we do when we apply HF methods and tools to providing assurance for complex signaling systems or human machine interfaces related to signaling systems like a train control system, where we found that human error analysis is quite effective for really exploring the different functions of the system. How does it behave? What are the classic errors? What tasks are there that are of a high criticality? So tasks with a high safety consequence or a high operational impact if they're performed incorrectly. What types of errors, and what are the types of consequences coming from those errors? So from that perspective, the HA is quite a powerful tool for doing that. Especially when you have, as I mentioned earlier, low fidelity inputs like static images, or where you don't have really a robust environment where you can really delve into and work through dynamic scenarios. So I think one of the key learnings here is, where possible, scope it out from the beginning to have high fidelity environments where you can really put users in front of it, or really conduct workshops around these types of environments to elicit that feedback from the users and interpret the design. So that's one of the main things. I know there's projects out there that have been good at doing that. Sometimes it depends on the size of the project, but yeah, if possible, and that there will be an HMI element to a project that is novel or complex, then really baking that into the contract and having a dynamic environment is really critical to that. Another lesson learned is around feedback from end users. So how do you elicit feedback from end users for these types of systems where you don't have, to the first point, where you don't have these dynamic environments? How do you really work through these scenarios, and how do you talk about these things where you can actually get valid feedback and robust and constructive discussion around it, where you really we're all talking about the same thing, system behavior, and really understanding what's happening with the system and where things can go wrong. Again, that really comes down to what are the inputs that you get when you come into these types of projects. What's the level of fidelity? What's the extensiveness of those inputs? In our case, we had to do we did engagement with the signaling engineers to really work through and understand for ourselves as well, how does the system work? And really for the signaling design engineers as well, identifying all these potential use cases and system behaviors. There was quite a lot of back and forth and work that went into that before we even got to the point of engaging with end users. So again, one thing to think about. And then I think the third point kind of really talks to that as well. Can you include that in the scope of the contract? Things like that. So visualization materials or environments to really work through. You can tell that we're hammering this point home because we really were working with static images, and we were using Paint and PowerPoint to drag and drop and color dropper things. So that definitely made it a challenge. Don't know if you wanted to add anything to the lesson plan, Kate. No. I think we're at time. Are we, Fiona? We have a few minutes left.
We've got time for some questions. Thank you so much for that presentation. It was a bit of a deep dive into the detailed analysis that can be undertaken to help get that alignment between, system design and performance, and user tasks and goals as well, which is really good. And even with static images, you still got some good design outcomes. So we can work with what we've got to still get some good human factors outcomes for the end users, which is good to hear. There is one question, which is a shout out to the work you guys have done on this project, but also a question around learnings from dealing with human factors integration with the signalling and train control system engineers. How do you work effectively with that group, and how do you utilise them to get those good outcomes, particularly when you're working in projects with alliances and things like that, where you have got competing motivations and goals? How did you sort of see that working really effectively on this project?
So I think the effectiveness for us was really coming in and demonstrating the value of human factors and where we could provide or apply the structured approach that we brought in, with the human error analysis in particular, and working through the scenarios where that really built up, as I mentioned earlier, not just our understanding, but also the signaling design engineers' understanding and the alliance's understanding of how does the system work, what are the use cases, what are the user interactions here, how is the system behaving, and then building that strong foundation of that common understanding of the system. That then helped us identify the pain points and the potential for error, and where the design could potentially be improved to then provide that improvement for the end users. And we brought that into the workshops with the end users as well to really then talk through those things. So that was
Can I add to that?
Yes, please.
Peter's question came in just before, so thank you for the question, Peter. And Peter's question came in just before the final slide, which was talking to lessons learned. And but it's one of the reasons why we talk about the scope and the contracts. A common experience that we found on these projects is that it's the HF practitioner, i.e. us, often making the case to project managers, engineers, the engineering team, that where the design is novel or complex, there is value in doing this work. And once the engineering team work with you, obviously we rely on them to do this work. Jan's demonstrated a high level of signalling knowledge, which you have to try to gain when you're working on these things. But we can't do this work without them. So it's teamwork. But the first time when they realise that you've identified something that they haven't identified themselves, then it obviously becomes much easier. So it's why we've ended though with the plea on behalf of I think all HF projects. The more specific we can be about what the activities are, the less effort the HF people on both sides, and thank you for your support, Peter, on the project. Thanks, Peter. But on this particular one, the less effort that it leaves to HF practitioners to have to make that case. So.
Yeah, that's good. And I think it's a nice segue into the next presentation we're going to have after our break around the importance of integrating human factors into change, and particularly right at that early stage around defining what is the work that actually needs to be done and what form should that take to be effective, whether that's, using more dynamic simulations or modelling and design and working in more of a sort of prototype or live environment with users so that they can see what the change is rather than working off static, drawings and wireframes, which can still get good outcomes. But, as you say, there's that risk-based approach to, if this is a significantly novel change or a big step change, there's definitely benefit in putting that effort in. Thank you both for your time.
Thanks, Fiona. Thanks, everyone.
And thank you, everybody, for joining us for that middle section of our presentation.